Okay, let's begin by looking at what we should already know. We should know that we can describe a parabola in terms of a Cartesian equation, like this x squared equals 4ay, where that will give us a concave up parabola whose vertex is at the origin and whose focal length is this value a. And so the focus for the parabola should be at 0, a, and the equation of the directrix, which will be down here, will be y equals minus a. Similarly, we can also describe the parabola in terms of a pair of parametric equations, where we can describe x as 2at, where t is the parameter, and y equals at squared, where again t is the parameter. And similarly, we can describe any point on the parabola, let's just call this one P, as a pair of parametric representations, 2AP, AP squared. So instead of describing the point as x comma y, we're actually describing the point in terms of the parameter. We can investigate things like the gradient of the tangent drawn at P on this parabola. And so in order to do that, we need to use calculus. And in order to do that, we need to differentiate this equation. So let's rearrange it so that y is the subject, and then that allows us to differentiate it. And we will get 2x over 4a, which simplifies just to x over 2a. Now, at this particular point P, the value of x is 2ap. So if we substitute, sorry, that should be like that. If we substitute in the value of 2ap, then y dash, which will be the gradient of the tangent to the curve at the point P, will be 2ap over 2a, which just simplifies to P. And this is the beauty of describing a parabola parametrically, because the value that we choose, P, the parameter, is actually the gradient of the tangent to the curve at that point. So to summarise what we found, if we have a parabola x squared equals 4ay, we can rearrange that to make it into y equals f of x format and differentiate it to find the gradient of the tangent to the curve at the point 2ap squared, and the gradient of the tangent there is p. But what if we wanted to find the equation of the tangent to the curve at the point p? Well, we'd use y minus y1 equals m x minus x1, and we'd use these coordinates for the point, and so substituting in those values, y minus ap squared. Now the m value we decided up above was just p, so the m value is p, and substituting in the value for x1, it would be 2ap. Now let's just tidy that up by expanding, and we'll get px minus 2ap squared. And if we combine like terms by adding ap squared to both sides, we will just get y equals px minus ap squared. That's in y equals mx plus b format. If you'd like it in general format, you could subtract y from both sides, and that would be the equation in general format. So y equals mx plus b format, or in general format, that is the equation of the tangent to the curve, x squared equals 4ay, at the point P, 2ap, ap squared. Just like we were able to work out the gradient of the tangent to the curve drawn at P, and also the equation of the tangent, we should also be able to work out the gradient of the normal drawn at P, which is perpendicular to the tangent, and also its equation. So that's what we'll be doing next. And we'll be making use of the fact that for perpendicular lines, m1 times m2 equals minus 1. And so if the gradient of the tangent is p, then the gradient of the normal should be the negative reciprocal of that, which will be minus 1 over p. And we can use that fact to in conjunction with the equation that we use to find the equation of a straight line, and using the coordinates of the point that is on the normal to work out the equation of the normal. So substituting in the values of the point, we would have y minus ap squared equals m x minus 2ap. And multiplying both sides by p, we'll get py minus ap cubed equals, and expanding that negative out the front, minus x plus 2ap, and that can be rearranged into general form as x plus py minus 2ap minus ap cubed equals 0. So, in summary, we can describe a parabola using a Cartesian equation or as a pair of parametric equations. We can describe a point on the parabola in this way using the parameter p, 2ap, ap squared. The gradient of the tangent drawn at the point P, it's given by just the parameter P, and the equation of the tangent drawn at P is given by this relationship here in general form, but we could also give it in y equals mx plus b form. Similarly, we can find the equation of the normal drawn at P, where its gradient is given by the negative reciprocal of P, or minus 1 over P, and its equation is given by this relationship here in general form.